Here's the answer for page 55, the oral exercises. Number 1. We're given a set with 4 elements in it and another set with 4 elements in it. And for question A, we're asked to create the union of the sets. The symbol for union looks like this. When you make a union of sets, you create a set that has every element from both of the sets put together. So one of the elements is 2, and then there's 3, and then 4, and then 6, and then 8, 9, and 12. This is the union of 2 sets, a set that has all the elements from the sets put together. Notice that 6 appears in both sets, but you only write it in the list one time. Now we're going to create the intersection of the 2 sets. The symbol for intersection is the upside down U symbol. This is a set with numbers in it, but the intersection of 2 sets is a list of the numbers that are only in both sets. So is 3 in both sets? No, it's not. Is 6 in both sets? Yes, so you include 6 in the intersection. What about 9 or 12? Is 2 in both sets? What about 4? What about 8? The only element that is in both of the original sets is the number 6. So our intersection of the 2 sets is only that one element, the 6. Now number 3, we have 2 different sets of numbers with elements in there. And we're asked for the union of the sets. So this is a set with elements in it. And the union has all the elements from both of the sets put together. So there's a 2 and a 4 and an 8. The intersection is all the elements that are in both of the sets at the same time. 2 is in both of them, 4 is in both of them, and 8 is in both of them. So in this case, the union set and the intersection set are the same thing, but that's not common. Number 7, we're given 2 sets of numbers. The first is the even integers. Those are numbers such as -2, 0, 2, 4, 6, and so on. The other set is the natural numbers. Those are the numbers 1, 2, 3, 4, and so on. Let's first create the union. We're going to make a set and figure out all the elements in the set. It's everything from the first set along with everything from the second set. So we have some negative numbers from that first set that we would put in here, such as -4, -2, and so on moving to the left. We also have the number 0 from this first set, and the 2, the 4, the 6, the 8, and so on. But along with that, we're going to have all the elements from the second set, which starts at 1 and counts upwards. So we want to have 1, 2, 3, 4, 5, and so on forever. This set is the union of these 2 sets. It contains all the elements from the first set along with all the elements from the second set. Now the intersection. What are the numbers that are in both of the sets at the same time? Well, none of the negative even integers are in that second set, so we don't want to include those in the intersection. We can't include 0 because it's not in the natural number set. We can include the number 2 because it is in this first set and it's in the second set. We can also include the number 4 because it's in both sets, and the number 6 and the number 8, and so on forever. Now page 55, the written exercises. We're asked to create graphs of some absolute value expressions. And the key to doing this is to transform the absolute value expressions into expressions that do not have the absolute value bars. there are three situations you look for, and it all depends on what symbol you have here: a less than, a greater than, or an equal symbol. In this case, we have the less than symbol. The way that this is transformed into an expression without absolute value bars is to take the opposite of this number, which is -2, to keep that less than symbol, to take the expression inside the bars, which is x, to write down the less than symbol again, and take this number here, the +2. So notice on the left we have the negative of this original number, whereas on the right we have that original number. In the middle between those arrows, we have the expression that was in the bars. All right, the letter x is isolated in the center of this expression, so this is simplified. Let's make the graph of this. Find -2. It gets an open dot because there's no equals to on that symbol. To the right of that is +2, and it gets an open dot. The letter x is sandwiched in between those two values, and so you would shade all the numbers in between those two values. This is a graph of this original expression. Now, number 3, we have an absolute value expression, this time with an equal symbol. So the way that you rewrite this so it does not have bars is like this. Take the expression in the bars and set it equal to the opposite of this number on the right, which is -7. Then write the word or put a union symbol. Write the expression in the bars and set it equal to this number on the right. When you look at both of these pieces, the 5 minus y was from inside the bars, and this number here is the negative and positive version of the original number on the right. Now let's solve both of these equations. First, we could subtract 5. We get -y equals -12. And then divide by -1. We get y equals +12. To solve this other equation, we're using those same two transformation steps. When you subtract 5, we get -y equals 2. And when you divide by -1, you get y equals -2. Remember, it's the word or connecting these two statements. So write the word or down. Now we can graph it. Y equals 12 is a dot on the number 12. Y equals -2 is a dot on the number -2. Number 5. To solve this absolute value equation, you focus on that symbol there to determine which of the three cases you have in order to rewrite it. Like the previous, this is an equal symbol. So the expression in the bars is equal to the negative of the 9. Then the word or. The expression in the bars is equal to the +9. Now solve each of these equations. First add 1. So we get 2x equals -8. And then divide by 2. X equals -4. Do those same two transformations on the other equation. When you add 1, now you have 10. And when you divide by 2, now you have 5. The word or is joining those two results. So to graph it, we have -4 with a dot and +5 with a dot. Number 7. To solve this absolute value expression, we rewrite it so it does not have the bars. To do that, focus on what symbol you have so you know which situation to use. This is a is greater than symbol. The way you rewrite this is to write the expression in the bars, to change the symbol to less than, and take the opposite of that number, -3. Then write the word or. Take the expression in the bars, keep the greater than symbol, and keep the +3. The y minus 4s were the expression inside the absolute value bars. For one of the pieces, we're switching to a less than symbol and taking the negative of the number on the right. For the other piece, we're keeping the greater than symbol and keeping the positive number that was on the right. Let's solve each of these by adding 4. So we get y is less than, and negative 3 plus 4 is 1. When you add 4 over here, you get y is greater than 7. It's the word or that connects these two parts together. Now we can graph them. Here's 1, and it gets an open dot and shade less than 1 to the left. Here's 7. It gets an open dot and shade greater than 7. That is to the right. Every number that's been shaded is a solution for y in this original expression. Okay, number 9. This has a less than symbol. So to rewrite it, you take the negative of the number on the right, copy down that less than or equal to, put the expression that was in the bars, put the less than or equal to again, and put positive 1. The expression from in the bars gets sandwiched in between the negative and positive version of this number on the right. Now let's solve this. Subtract 9 from all places in this expression. Negative 1 subtract 9 is negative 10. Here in the center, when you subtract 9, the 2y is left over. On the end, when you subtract 9, you get negative 8. To get the letter y alone, we have to divide by 2 in all places in this expression. Negative 10 divided by 2 is negative 5. In the middle, when you divide by 2, the letter y is alone. And on the end, when you divide by 2, you get negative 4. We can graph this. Here's negative 5, and to the right of that is negative 4. Both of them get closed dots because the symbols have the or equal to bars. The letter y is in between those numbers, so you shade in between there. Number 11. This one has the greater than symbol. So here's how you rewrite it. The expression in the bars is less than or equal to the negative of the 3, or the expression in the bars is greater than or equal to 3. To solve this, we need to subtract the 2 away. We get negative 5h is less than or equal to negative 5. Over here, when you subtract 2, you get negative 5h is greater than or equal to 1. Now divide by the negative 5. When you divide by a negative, the arrow switches. Negative 5 divided by negative 5 is 1. Over here, when you divide by negative 5, the arrow switches. And 1 divided by negative 5 is negative 1/5. The word or connects these together. We can graph this. Here's negative 1/5. To the right of that is where positive 1 is. What kind of dots are they? They're both colored in dots. Where's the shading go? We want to be greater than the 1, so you shade to the right of the 1. We want to be less than the negative 1/5, so you shade to the left of that fraction. Number 13 changes the directions. We're asked to specify by roster, that is to list out all the solutions. We want to find solutions for the variable t such that these conditions are met. So just focus on this statement and solve it. Let's get the t alone in the middle by subtracting 5. Negative 8 subtract 5 is negative 13. There's a 2t alone in the middle. 11 subtract 5 is 6. Now we need to divide by 2. Negative 13 divided by 2 is the fraction negative 13 over 2. In the middle, when you divide by 2, the t is alone. Over here, 6 divided by 2 makes 3. This statement describes the solutions for t, but it doesn't actually list them out, which is what specified by roster means. For number 13, there was a little bit more to the directions, which was to only include integers when you make your list of numbers. So what integers work for t if t is in between these two numbers? To help us figure out the integers, it might be useful to change this fraction into its mixed number form. Negative 13 halves is the same thing as negative 6 1/2. Now we can find the numbers that are in between negative 6 1/2 and positive 3. Let's list them. Negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, and 3. All of these are the integers that work for t. Number 15. Let's find all the integers that work for t. First, we need to solve this for t. So we could subtract the 2. And we get 5 is greater than or equal to negative 5t is less than negative 15. Now divide by negative 5. We get negative 1 is less than or equal to t, which is less than 3. Notice I reversed the arrows because I divided by negative 5. Well, this describes the solution, but it doesn't specify by roster. So let's list the integers that satisfy this. The first number that works for t is negative 1, because it says negative 1 can be equal to t. We could also have 0, 1, or 2. For number 17, let's find all the numbers that work for g. First, solve this by adding 2. We get g is greater than or equal to 0. Now go over here and solve this statement by adding 10 to get 2g is less than 10, and then dividing by 2 to get g is less than 5. Furthermore, notice this symbol in the middle, which is the symbol for intersection. We want to list all the integers that work for g, and it has to satisfy these conditions. We want to have the intersection of integers greater than or equal to 0, and at the same time, they're less than 5. What are the numbers greater than or equal to 0, and they are less than 5? We could have 0, 1, 2, 3, and 4. For the review assignment, we go back to page 51, and we have an inequality which we're going to solve in graph. First, add 4. So we get 3y is greater than or equal to 18. Then divide by 3. So y is greater than or equal to 6. Find 6, put a closed dot, shade to the right. For number 4, to solve for t, we need to subtract the 7. We get negative 5t is less than, and 32 take away 7 is 25. Now divide by the negative 5. Switch the arrow, and we get negative 5. For the graph, that's an open dot and shade to the right. For problem 6, to solve for b, we first have to cancel the b term on the right side of the problem. Let's subtract b. 5b subtract a b makes 4b. Now we can subtract the 7. So we have 4b is greater than or equal to negative 8. Then divide by 4. b is greater than or equal to negative 2. There's a closed dot on negative 2 and shade to the right. The next review assignment is page 47, problem 8. We have an equation. We're going to solve and check it. First, subtract the 9n. so that there's no n term on the right side. 7n subtract 9n is negative 2n. Then add 6. So we have negative 2n equals negative 108. Then divide by the negative 2. Negative 108 divided by negative 2 is 54. To check that answer, you go back to the original equation and substitute 54 where the letter n is. Is that equal to this expression? Seven times 54 subtract 6 is 372 on my calculator. Over on this side, 9 times 54 subtract 114 is also 372. That answer checks. For problem 10, to solve for n, we might first multiply by the 3. Because if you times by 3 on both sides, the 3 you times by will cancel the denominator of 3. We now have 5n equals 180. Now we can divide by 5 on both sides. 180 divided by 5 is 36. To check that, substitute 36 in place of the variable. Is that equal to 60? Take a calculator, multiply these together, and divide by 3, and you'll find out that it is 60. The last question. To solve for x, we might first multiply by 7. Because if you do that on both sides of the equation, the 7 that you times by will cancel the denominator of 7. 7 times 3.5 makes 24.5. That's equal to 2x. Now we can divide by 2 on both sides. The answer is 12.25 is equal to x. The final thing to do is the check. Is 3.5 equal to 2 parentheses 12.25 divided by 7? Take a calculator and times these together, then divide by 7, and you will get 3.5. This checks.